This right here is a picture of Henrietta Swan Leavitt. And she made a little over 100 years ago, this is in the early 1900s, while working for Edward Charles Pickering, who was a Harvard astronomer, while I was working for his observatory, she made what is arguably, well, definitely one of the most important discoveries in all of astronomy, and probably, I would say it ranks their top three because it really enabled people like Hubble to start realizing that the universe is expanding, or even being able to think about how to measure distances to objects in space well beyond the reach of our tools with parallax. We saw with parallax you have to have extremely sensitive instruments just to even measure distances to stars relatively close to us. Very sensitive instruments to get to stars maybe further out into our galaxy. And we don't have the instruments even today to measure things beyond our galaxy. But because of Henrietta Swan Leavitt, we were able to approximate or get good senses of the distance to objects beyond our galaxy. So let's just think about what she did. So her job was literally to classify stars in the large Magellanic, I have trouble saying that, Magellanic Cloud and the small Magellanic Clouds. And this is what they look like from the southern hemisphere. This is the large right over here, and that this is the small right over here. And remember, this is before Hubble realized that there, or showed the world that there are stars beyond our galaxy, that there are galaxies beyond our galaxy. So at this point in time, people didn't even fully appreciate that these were separate galaxies. We just said, hey, these are kind of these blobs or these clusters of stars that we see in the southern hemisphere. And just to get a sense of where they are relative to our galaxy, the Milky Way galaxy, this is obviously not an actual picture. We can't take a picture from this vantage point. This would have to be very, very far away. But this is the Milky Way right here. And this is the small Magellanic Cloud. And this is the large Magellanic Cloud. I'm getting better at saying it. So her job was literally just to classify the different stars that she saw. But while she was classifying, she looked at these things called variables. And it turns out what she was looking at were a class of stars called Cepheid or Cepheid variable stars. And what's interesting about them is two things. They're super duper bright. They're up to 30,000 times as luminous as their sun. And they're 5 to 20 times more massive than the sun. 5 to 20 times the sun's mass. But what makes them interesting is, one, they're really bright, so you can see them from really far away. You can see these Cepheid variable stars in other galaxies. In fact, we can see it well beyond even the small Magellanic Cloud or the large Magellanic Cloud. But you can see these stars in other galaxies. And what's even more interesting about them is that their intensity is variable, that they become brighter and dimmer with a well-defined period. So if you're looking at a Cepheid variable star, and this is just kind of a simulation, a very cheap simulation, it might look like this, and then over the course of the next 3-4 days, it might reduce in intensity to something like this, and then after 3-4 days again, it will look like this. And then it will look like this again. So its actual intensity is going up and down with a well-defined period. So if this takes 3 days, and then this is another 3 days, then the period, one entire cycle of its going from low intensity back to high intensity is going to be 6 days. So this is a 6-day period. And what Henrietta Leavitt saw, and this wasn't an obvious thing to do, she assumed that everything in each of these clouds are roughly the same distance away. Everything in the large Magellanic Cloud is roughly the same distance away. And it's obviously not exact. This is an entire galaxy, so you have obviously things further away in that galaxy and things closer up. You have stars here, and their distance isn't going to be exactly the same to us, though we're sitting maybe over here someplace. But it's going to be close. It wasn't a bad approximation. And by making that assumption, she saw something pretty neat. If she plotted, so let me plot this right over here. So she plotted on the horizontal axis, if she plotted the relative luminosity. So really, the only way that she could measure this is just how bright did they look to her? And she's assuming that they're same distance. So obviously, if you have a brighter star, but it's much, much further away, it's going to look dimmer. So if you assume that they're all the same, roughly the same distance, then how bright it is will tell you how bright it is at the actual star. So she plotted relative luminosity of a star on one axis, and on the other axis, she plotted the period of these variable stars. She plotted the period. And what I'm going to do is I'm going to do this on a logarithmic scale. So let's say that this is in days. So this is 1 day, this is 10 days, this is 100 days right over here. It's a logarithmic scale because I'm going up in powers of 10. I could say that if we say if we take the log of these, this would be 0, this would be 1, this would be 2. And so that's what I'm using as a scale. So I'm using the log of the period, or I'm just marking them as 1, 10, 100, but I'm giving each of these factors of 10 in equal spacing. But when you plot it on this scale, the relative luminosity versus the period, she got a plot that looks something like this. And this is obviously not exact. She got a plot that looks something like this. It was a fairly linear relationship when you plot the relative luminosity against the log of the period. So this is obviously a logarithmic scale over here. And so you could fit a line. And why I'd argue, and I think most people would argue, this is one of the most important discoveries in astronomy, is if you know, because think about what the problem here is. We can look at all of these stars in space. We can look at, let's say you look at a fraction of the sky and you look at something that looks like that. So it's really bright. And then you see something dim that looks like that. So if you have a very superficial understanding, you say, oh, this star is brighter. You would say that this is a fundamentally brighter star. But how do you know that? Maybe instead of being brighter, maybe it's just a dimmer, closer star. Maybe this is a closer star. Maybe this is an entire galaxy, but it's so far away that you can't even tell. But all of a sudden, if you by the work that Henrietta Leavitt did, if you see one of these Cepheid variable stars in another galaxy, you know its relative brightness compared to other Cepheid variable stars. And so if you can place just one of these Cepheid variable stars, if you know exactly the distance to one of them, and then you know its absolute luminosity, you then know the absolute luminosity of any other Cepheid variable stars. So let's say using parallax, which is our other tool, we find, let's say there's some star in our galaxy. And let's say using parallax, we're able to come up with a pretty good measure that it is, I don't know, let's say it's 100 light years away. Light years. And this star is a Cepheid. This is a Cepheid variable star. And let's say its period is 1 day. It's 1 day. So we now know something interesting. We know variable stars with a period of 1 day at 100 light years away will look like this. Will look like this drawing right over here. So if we later on see a Cepheid variable star with a period of 1 day, so it gets brighter and dim over the course of 1 day, and maybe it's redshifted as well, but maybe it looks a little bit dimmer. It looks like this. We now know that if it was 100 light years away, it would have this luminosity. So based on how much dimmer it is, we can then figure out how much further away this Cepheid variable star is. If that confuses a little bit, I'll do a little bit more details in the next few videos so we can get a closer sense of how the math would work. But this was a big discovery, just discovering this class of stars, this Cepheid variable class. She wasn't the one who discovered them. People knew before her that there were these stars that got brighter and dimmer. But what her big discovery was is seeing this linear relationship between the relative luminosity of these stars and their period. Because then, if we see Cepheid variable stars in completely different galaxies or galactic clusters, by looking at their period, we know what their real relative luminosity is, and then we could guess how far those things really are. We could estimate how far those things really are.